Hi everyone, and today we have Tim Van Dam from Delft University, who is going to present a talk about enriching source code with contextual data for code completion models, which is a study that was presented at the last MSR, and which talk I had the privilege to attend. And one nice feature that I wanted to mention is that it's done for TypeScript, which is not always the language of choice for researchers and practitioners who work for on code completion. And yeah, we are very happy to host Tim. So Tim, what's your preference? Are you okay with having questions during your talk, or would you like to have them afterwards?
I'm fine with questions during the talk.
All right, so then I'll keep an eye on you folks asking questions. So please raise your hand or write in the chat if you're not able to ask a question by voice. And I think that in one moment we should start.
All right, so you want me to start now? Or do you want to wait a moment?
Okay, just give me a sec. I'll check out the visitors. I think
we should start.
Yeah, we're pretty stable on the number of visitors. All right, so yeah, please, Tim, you have the floor.
All right, sounds good. Thank you. Well, first of all, thank you for inviting me, of course. I'll quickly introduce myself. So I'm Tim Van Dam. I'm currently a master's student at TU Delft. And well, as Michel already said, I'll be presenting the paper I presented at MSR this year. This paper all started with my bachelor thesis when I worked with my supervisor, Malia Izadi, on investigating how code completion models use contextual data that is included in the code to make their predictions. Yeah, we expanded on my work during my bachelor thesis and eventually made this into a conference paper, which we presented. Yeah, my paper is called Enriching Source Code with Contextual Data for Code Completion Models and Empirical Study. As I said, me, my supervisor, Malia Izadi, and Dr. Professor Arie van Deursen, all from the TU Delft AI for Software Engineering lab. So let's see. So before I start my talk, I'll quickly give an overview of what I'll discuss. So I'll start with how I currently see code completion, so what we have and what changes are happening and what we can do with these changes. Then I'll explain relating to this why this study is relevant, after which I'll explain the research questions of this paper and the experiments we conducted, after which I'll present the results, the findings of these results, and their implications. And then finally, I'll go into future work and yeah, what we can do in the future and what has already been done. So let's start with the basics. Well, as this is a JetBrains seminar, I'm sure you're all familiar with the traditional IDE code completion, where you type out something like, well, as it says here, cookie dot, and well, then the code completion is able to easily find out what functions exist on this cookie object and give you a list of suggestions. Well, this is very powerful for one specific reason that is different from the modern code completion with language models that we're seeing right now, because this is very good at taking into account the context that is within your project and within your third-party dependencies. So this cookie object, it's all imported from the cookie library. And it will always be able to give me the correct functions that we are sure that exist within that library. If we have a look at the current LM-based code completion models, this is not the case at all. So instead of getting a list of the members of the cookie object, we now put our text into this black box and we get some text out of it. But what does this black box actually do? Well, it doesn't look at the properties of the cookie object. It just, well, does some calculations and manages to find out that parse cookie header is most likely, according to the model at least, to be the correct continuation of this input. So one thing that we have lost in this transition from the traditional IDE code completion to language model-based code completion is the fact that the local context is no longer considered. And this is something that is not great to have lost, because while training data can, of course, give you a lot of information about commonly used third-party dependencies, you're still losing a lot of information when you're working on proprietary code or wanting to use code and functions that are created within your own project. So you're losing all this information, which will, of course, be great to have even in these language-based model-based code completion models. So to get to the motivation of this study, the problem I identified is that these current language model-based code completion models are not context aware like the traditional IDE code completion is, which is a problem. So when you think about it, we could solve this quite easily by simply giving these language models input that includes all the context we wanted to have. So we do in-context learning pretty much. We give it all the code and that it is, well, able to use, and then in the output, hopefully it uses our own code. Now we can do this for our own project, but also for third-party dependencies. But well, quite quickly, you'll think about it and you'll see, oh wait, we have a limited amount of tokens in our context size. So can we actually do this? Well, I've listed out here a couple of models. So GPT-3, GPT-4, and a bunch of code completion or models that can be used for code completion. As you can see, the number of tokens is generally not too high. So we have GPT-4 with 32,000 tokens. And you may think that this is very high and that, well, we can provide a lot of context to this model so that it is able to give us suggestions that really take into account what we have done in our own project so far. But when you look at this in practice, this may not be the case. So let's have a look at what we could do. What we could, for instance, do in the context of TypeScript is give a lot of type information to language models for code. So what typically happens in TypeScript is that you create your code in TypeScript and then compile it, which will give you two different files. And one file will be JavaScript code without any type information. And another file will be a declaration file where all the type information is stored, which will allow consumers of that JavaScript bundle to still have type information. So what we could try to do is give this type information without the code to language models to make sure that we're not giving the whole code. So we're already removing a big part of this input by only using the type information. We could try it that way to make language models more context aware. So let's have a look at how we could do this in a TypeScript project where we create a small web API, HTTP API using Express and Node.js. So the question is it feasible to do this with type information? Well, let's start off with Express. If we have a look at the type information and we tokenize it all using well, one of the tokenizers I used in this paper, we already have 1,044 tokens. Well, if you have a look at the previous slide again, well, there we go. Unix Coder and CodeGPT, they don't have enough tokens, so we already lost 2 models. And the other models, well, they have twice as much tokens or even more, but it's likely that we're going to not be able to use these models either if it keeps growing like this. So, well, next up, we want to be able to use cookies. So, well, we have the cookie package again, 1,500 tokens. And you can see at the rapid rate, this is only type information, but it's just too many tokens to be able to feed to these models all at once. So next, we want to have a database. So we have the Postgres library. Well, it gets even worse. Then we want to do testing. Well, 18,000 tokens. It seems like GPT-4 with 32,000 tokens won't cut it either if we keep going like this. Because, well, if you're working with Node.js, the amount of dependencies per project is always pretty large. So we're only at 4 right now. It probably won't ever work in a project that is not a pet project. And then we also have types for Node.js itself, which includes, well, all sorts of native standard library functions. Then we have 2.5 million tokens, so this is definitely not going to cut it. Of course, the most important thing is probably your own code, which is all going to depend on your project as well. But yeah, we don't know how much that is. Now, this is a bit of a contrived example because the common libraries like Express, they're so common that they are very likely to already have been in the training data. And this is good because, well, that kind of solves an issue, right? And the same goes for PG. It's a very common libraries and Jest as well. But, well, what if the API of this library changes? Well, then we cannot use it anymore. We can retrain the model perhaps, but well, that's pretty expensive. So that doesn't seem like a logical thing to do. Now, another reason why this example may not be a very good example is that we can, of course, filter this down a bit more. We can perhaps apply some, create a model that somehow filters this down even more, depending on how you're trying to do code completion. But overall, the point still stands because this is only type information, and there's so much information in an IDE that code completion in traditional IDEs can use that is still not being used here when trying to give the language model more information. So this is generally the motivation. We simply cannot feed enough information to these language models yet to make them fully context aware. What we can do is we can train them again, but that's expensive. So what can we do to fix this? Well, one of the things we can do is simply expand the context window. It's a pretty straightforward solution, but it may not be perfect. And it definitely it is definitely not something that we can do infinitely, right? Because if we get projects that keep getting bigger and bigger, and we need context windows that get bigger and bigger, well, we can't do that infinitely, probably. And another problem with this is that a recent paper has investigated how we can imply in-context learning or few-shot learning when the context is very long. And it turned out that especially the information at the beginning and at the end of the context window is used properly by these models, well, which presents an issue when we want to use very long context windows. Because what happens is that a lot of information in the middle might simply not be used, and maybe the models, they simply can't use it properly yet. So this is still an issue with simply trying to expand the context window. So what we're trying to do with this paper instead is to reduce the noise that's present in the context. So pretty much instead of providing as much information as possible and hoping that this model will be able to figure out what is relevant, we simply make sure that we only provide valuable information. But in order to be able to do this, we must, of course, be able to measure how valuable specific information is. And that is exactly what we're trying to do. So in order to do this, we selected 2 different types of information that we could perform our experiments on to start with. And these types of information were type annotations and different types of comments. So this led to the following research questions, namely, how does the number of available type annotations affect performance? And how does the presence of different types of comments affect performance? So these are really basic forms of information that you will find in pretty much any code, as long as it is able to have type annotations, because that's not possible in dynamically typed languages, of course. But there's, of course, a lot more information that you could consider in the future. So first off, type annotations. Well, many languages use type information to make the language more strict to prevent runtime errors and to instead raise these errors at compile time. This is great when you're a developer because you'll catch these errors early on and you won't have to deal with this behavior of sudden crashes in the runtime. And this is also very useful to traditional code completion in IDEs. Because what you can do then is you can have a look at the local scope, see what is the type of all the variables, and then look through the index with all the available functions, and you can see do we have a function that takes arguments with the types that we have available in the current context or in the current scope, I mean. And this makes it possible to prioritize suggestions in such a way that it sort of matches what you are trying to do in the current scope. But since these language models for code do not give you context-aware suggestions, this is not really a thing. So do we really need these type annotations? Do we really need this generic T, value T, node 3, node T? Well, maybe not, because these language models, they work fine on dynamically typed languages as well, right? For instance, if we look at JavaScript, it is simply TypeScript without types. And we see that many language models are very capable at writing JavaScript. So perhaps we can just remove these type annotations and we'll have a model that is maybe just as good, but we don't have to feed it as much tokens in the context window, which makes more room for other types of information which can improve the performance of these code completion models. Now, for research question 2, we looked into comments. So we realized that there are many different types of comments, and they all have different uses, and they're not all useful to everyone or to every actor in a scenario. For instance, single line comments, which you see in the top image, well, it makes it easy for the developer to quickly, at a glance, know why something was done a certain way. So we see that we're removing a cookie here. Well, we can easily read, well, we do that because the cookie is invalid. But does a language model need this? I don't know. I don't think it's necessary. And the same goes for the second type of comment, which is a doc block. This doc block, it gives a high-level description of what the function is supposed to do, and can explain how you're supposed to use this function. So you say we have these parameters. In this case, we are working in TypeScript, so we don't specify a type. But in JavaScript, what you could do is you could say what the type of the parameters are. You can give a nice description to all of these parameters. You can explain what the return type is and give examples. Well, this makes it very friendly and for the developer to use this method. But this information is all quite obvious if you read the code as well. And well, reading such a comment may reduce the mental strain for the developer, but these language models, they don't really have an issue with reading the code. So why not just remove this comment? And well, I think this language model will be able to understand the code just fine and infer the exact same information. Now, the third type of comment is the simple multi-line comment, which is similar to a doc block in that it is multi-line. However, the data in it is not presented in a structured fashion, not as structured, because this is typically just natural language. As you can see in the bottom example, this is a method that solves some algorithm, and you have some input that is described in this comment, as well as the solution that is described in this comment. And well, language models could be able to read this and know, okay, I need to translate this into code that parses these input and then implements this this recurrence equation to solve it, well, which may actually be useful to this language model. These comments often help developers, but do language models really need it? That's what we want to investigate, and we specifically want to have a look at each comment type to see whether we can remove some of them to make room for other types of information. So to do this, we have an experiment pipeline. We start off by collecting a data set. As said earlier, we use TypeScript, which I'll explain a bit later, our choice. Next, we use this data set to create test, train, and validation sets with different information. Now, what we mean with different information is that we create variants of this data set where there are certain types of comments. So we can test in isolation whether single line comments have some benefits over multi-line comments, for instance. And then using these different variants of our data, we fine-tune code completion models and run them on test sets with these specific types of information. We can then use the predictions by these models to compute some metrics, which we then use for to check whether there's significant differences when we have specific types of information present or not present. And if this is statistically significant, we also numerically compute the effect size to see how big this improvement is, which allows us to simply compare how much different types of information is worth to these models. So let's start with the dataset. For the dataset, we chose to gather the top start GitHub TypeScript repositories. Initially, we were already trying to investigate type annotations because, well, they're so powerful when you consider traditional IDE code completion, but they're not really, they don't play a central role in language model based code completion. And quickly the decision was made to use TypeScript as it has a very powerful compiler API, which makes it very easy to remove these type annotations, but also to add these type annotations, which allows us to do a bit of a broader research into what the value of these type annotations actually is. So perhaps if we introduce more type annotations to this code, it could get better. So yeah, this is why we chose TypeScript over something like Python, for instance, because Python can also have type annotations. However, it does not have a very powerful compiler API, and it is not as strict with its types, which also makes it harder to gather data, as not a lot of Python data actively uses types throughout all the code. So we gathered 1,000 repositories from GitHub. However, it returned some duplicate information, duplicate repositories. And we also had to remove repositories that was in the training data of the models we used to prevent any bias in the test set. So we were left with 704 repositories containing 174,000 TypeScript files, which amounts to 26 million lines of code. And then we do some dataset processing. So this is really where the key of our research lies. Because we want to see what is the effect of the presence of type annotations and what is the effect of specific types of comments. So in order to assess this, we have to create the multiple variants of our dataset. So the first thing we considered was adding and removing type annotations. So yeah, TypeScript has optional types, which means that if you declare a variable that is very clearly a number, it will just know that it's a number and you don't have to say that it is. And this is why when we look at the original data set, you see that it has a 31% TE. And this TE is what we call a type explicitness, which refers to how many type annotations the code has. So it's simply how many annotations are present in the code divided by how many there could be in total. So we see that in 31% of the cases, type annotations were actually provided. But well, we want to investigate whether types are worth anything. So we create another version of this data set where we have removed all the types, leading to a 0% type explicitness because, well, there's no type annotations present. And we do the same thing, but instead of removing types, we use the TypeScript compiler type inference engine to add additional type annotations to the code to see whether maybe type annotations do actually help. And if we have more type annotations, perhaps we can increase performance over the original code, which only had type annotations every now and then. So we similarly did some processing regarding the comments. So we had different variants, one with all comments, one with no comments at all, and then we considered only using single line, multi-line, and doc block comments. A crucial thing in our data processing is the way we created the test set, because we really wanted to test the effect of each type of information in isolation without the possibility of anything else interfering. So the ideal way we thought of doing this was to have paired samples that we could then use in a statistical test, where one sample, both samples would practically be the same input. However, one sample would have more information than the other. So for instance, we would have one input which has no type annotations, and then one input where we add some type annotations. And since these inputs are identical, except for the presence of type annotations in one and not in the other, then we can test in isolation what really the effect of these type annotations is. So in order to do this, we had to be careful with our test set creation so that we can actually use a paired analysis on this. So the way we do this, once again, leverages the TypeScript compiler API. And the principle is quite simple. Namely, we first start with some code where we want to convert this into some test example that we will feed to our models later. So in practice, we want to convert this to an input and an output. Our first step was to determine where we are going to do code completion. And we'll do this by inserting a marker. So this marker is just a very simple TypeScript comment, which effectively means that we are just adding an element to this abstract syntax tree of this function. And this makes it very easy to modify this function without losing track of where we want to perform code completion. So we can do all sorts of transformations to this abstract syntax tree. And in the end, the comment will still be in the same position. So if we do transformations, different kinds of transformations, then in the end, all end variants will still have the same output, but the input will have undergone some transformation. So as an, yes?
Sorry, maybe you want a little bit later. I think it's a nice point to have a question from the chat, which is, have you tried to test effect of wrong type annotation deliberately injected?
That's interesting. We haven't done any research in that regard. However, during the creation of the different options with the different levels of type explicitness, in order to do this, we also had to support types from third-party dependencies. So there were already cases where these third-party dependencies were no longer available, which led to missing type information. And in these cases, I guess the scenario is comparable to a situation where you would have incorrect type annotations. And what happens then is that the TypeScript compiler simply crashes. So if we were to try to provide incorrect type annotations, it simply wouldn't work. And yeah, for that reason, the type annotations, they were all correct in this case.
But as a follow-up, I wonder, maybe it is like, maybe is this possible to provide a type annotation which is, I don't know, less broad than like than needed or stuff like that, so it would probably formally fulfill the requirements, but of the compilator, but still will be in essence wrong. I'm just not entirely sure how TypeScript compilator works, how strict it is.
Yeah, that is definitely possible. You have the any type, so if you give it type any, you can do whatever you want with it, and the TypeScript compiler will never complain. So this is definitely a valid concern. We actually did not look into how often the any keyword was used within our data set. But you can imagine that if any is used in some place inside of a project, and you run the type inference engine, that any would end up at other places as well. So this is definitely a good point. And we did not consider this, but this is definitely something that could be investigated in the future. Yeah, this all really depends on how you set up your TypeScript environment. You can allow the use of any, or you can disallow it. Usually it's disallowed, but if you allow it, then TypeScript will become closer to JavaScript, where you don't have any type annotations, which can then lead to runtime errors. But yeah, we didn't specifically account for this. So yeah, does that answer the question?
Well, it was not mine, but rather Timur who wrote that in chat. I don't have any further comments. Yeah.
All right. So then I'll continue. Right. So we left off here where we had just determined where we would want to do a code completion. And as I said, we can now do transformations to the abstract syntax tree corresponding to this function. And this comment, it will stay in the same place of that abstract syntax tree. So we can do transformations and end up with different versions that all want the same output. And I'll show you that right here. So the first image is the original, where we have type annotations as they were provided in the original dataset. Then we ran the type inference engine. And as you can see, we now have many more type annotations. So we have a return type, and every constant now has a type annotation as well. And in the last case, we removed the type annotation. So it is practically just like JavaScript, where you don't have any type annotations. And this allows us to easily create 3 variants of the same input, but with every input having a different amount of information embedded in the input. So this example shows how we do that for type annotations, but we apply the same process for comments as well. And this leads to 3 different test sets for the type annotation case, and let's see, 5 different test sets for the code completion case. And well, the thing is that this allows us to do that pairwise analysis that I was talking about earlier, because, well, we now have the same input every time, with the only difference being the information, which allows us to really, in an isolated manner, to test the effect of the presence of this.
I'm sorry, can I clarify a little bit? So how do you make sure that with the different type annotations, you have exactly the same examples for completion? So do you never complete the types, only the part of the line which does not contain types on the identifiers or some statements? Or how do you do it?
So you're talking about the output of the model, right?
Yeah. So how do you make sure that the right part is always the same?
Right. So we have some post-processing in place later in the experiment that tries to see whether the model tried to predict a type annotation, and if so, removes them so they are not compared to the ground truth, which has that same filtering function, because we really try to make sure that the type annotations are not in the expected model output. So in both places we try to prevent that. But this process is not perfect, so it is possible that some output has a type annotation in it, and in that case, well, we try to filter it if the model predicts it, so we still can get a valid metric out of it when comparing the ground truth and the prediction. However, this process is not perfect, so it could be that the case where we have added type annotations has a bit of an extra challenge, because it also has to add these type annotations in its output. But in principle, I don't think this really hinders our experiment, because we are working with TypeScript here, and in TypeScript, usually these type annotations are optional anyway. So perhaps if we see that that either adding types makes it better, well, then we have good news. But if removing types makes it better, well, then well, we don't have a problem either, because this will most likely work in TypeScript anyway.
Okay, yeah, thank you.
Yes. All right. So let's see. Right. So yeah, with these input-output pairs for each test set variant, we can easily compare and do a pairwise analysis to see whether versions with certain information do better than versions without that information. So next, let's have a look at the models that we use. So we selected 3 models. Of course, right now there's many newer models, but these models, they were selected quite a while ago. It was quite a while ago when we ran all the experiments. And back then they were the best we could do on our hardware. So first of all, we selected Unix Coder, which is a Roberta-based model by Microsoft. This model was first trained on natural language, so on English text from the C4 dataset, after which it was trained on Code SearchNet, which contains individual comment and functions in 6 different programming languages. Next, we also use the CodeGPT model, also by Microsoft. Now, GPT-2 is of course not by Microsoft, but Microsoft has a paper where they introduce CodeGPT. In this paper, they created 2 different CodeGPT models, one trained specifically for Python and one trained specifically for Java. However, as we are using TypeScript, we instead of using their models, we copied their architecture and trained a model ourselves using, well, their method, which is pretty much just to use GPT-2 as a starting checkpoint and then to train it on code. So yeah, that's our second model. And our third model is Encoder, which is XGLM based, introduced by a paper by people from Facebook. This is the model that's trained on the most amount of data out of the models we have here. It was first trained on Stack Overflow questions and answers and comments, which gives it the ability to understand text, in particular when it relates to code. Which I think is a quite interesting thing, because this is not something that is done by Unix Coder, which first learns English, not necessarily related to code, and only then tries to complete code. And Encoder was also trained on many repositories from GitHub with permissive licenses, which covered 28 programming languages in total. And this included TypeScript as well. And for Unix Coder, notably, it did not include TypeScript. But this is not a problem, because we will fine-tune these models ourselves on our own data with the different variants to see whether they can learn to predict some variant better than the other. So first, to do this, we do a grid search to find the best hyperparameters. After which we fine-tune Unix Coder and CodeGPT on each dataset variant, which we can then use for our evaluation. The reason that we did not do this for Encoder is mainly that the Encoder authors did not publish any code to further fine-tune their model. However, we decided to still try to use it, as its programming language just includes TypeScript. So we theorized that maybe it would still show consistent results. And in the end, we saw that the results were consistent with Unix Coder and CodeGPT. So we have included it in the results anyway, despite not fine-tuning it. So after having fine-tuned all these models on the different dataset variants, it was time to run inference to get answers for the test sets, and then to compute the metrics. So we use 5 different metrics. Well, if you've been to the seminar a couple of papers back, you will know that there are no great metrics to evaluate code. We also realized this, so we just decided to use many metrics in the hopes of them being consistent. And if they were consistent with each other, we could be pretty confident that that we could determine which which type of information is valuable and which is not. So we use exact match, added similarity, blue 4, rouge L, and meteor. Now, additionally, to ensure that potential differences in metric values are actually significant, we use the Wilcoxon-Silent rank test to make sure that small differences between metric values are actually significant. Because in the early stages of this research, we already saw that the differences in metric values were quite small. So concluding that one type of information is more valuable than another couldn't simply not be done without doing such a test. In the cases where this is where the performance differences based on the information was significant, we also compute the effect size so we can compare between types of information whether one is more valuable than the other. So let's have a look at the findings. First, for research question 1, where we considered the type annotations. Just a quick overview of the abbreviations. We have NT, OT, and AT, where NT is the no types dataset, OT is the original types dataset, and AT is the all types dataset, where we've added the type annotations. And in the table on the right, you can see that we computed the average metric values for our different dataset variants with different amounts of type annotations for each model. And immediately, it's pretty clear that the top row for each model seems to do best. So the version without any type annotations. Now, as mentioned earlier, this is not, to me, this is not too surprising, because these models are generally pretty good at static, dynamically typed languages anyway. So why wouldn't they do good at type language? Wait, I'm confusing myself a bit. So why wouldn't they do good in this scenario where we remove types? So we see that this indeed led to the best performance, especially for Unix coder. But interestingly, adding type annotations also seems to have a marginally positive effect. We can see that for Unix coder and for CodeGPT, that if we compare the version with 31% type explicitness to the version with 95% type explicitness, we can see that it actually gets a very small amount better if we just compare these metric values. But as I said earlier, these differences in metric values are not very large. So we should also have a look at the statistical analysis, which is displayed in this table. And well, don't try to read the entire table. I'll summarize it for you. All the metrics, nearly all the metrics show that there is a significant difference between the different variants of the dataset. And it's confirmed that indeed removing type annotations leads to a performance improvement for the 3 models. However, you should note that the effect small is relatively small, or well, it is definitely small for each of the models. So whether this has a practical use is something you can think about. And additionally, this analysis shows that the adding of types is also slightly beneficial. But once again, looking at the effect size shows that adding types is less beneficial than removing types. So how can this be? Why is it the case that having 31% type explicitness is worse than 0% type explicitness or 95%? Well, if we think about it, it is the case that the version with no type annotations and all type annotations is simply way more regularly structured than the other, than the original type version, where we only have type annotations in 31% of the cases. So there may be some inconsistencies in this, in the way that these type annotations are added to the code, which can make it more difficult for the code completion models to accurately predict what should follow. Additionally, why removing type annotations may be beneficial is simply because there's more room for source code. Because, well, if the model input is completely full and we remove the type annotations, then suddenly we make more room for additional source code, which could help these models generate better predictions. And additionally, as was slightly discussed earlier, and if you have these models predict types, you add a small bit of extra difficulty for these models because, well, they have to get the source code token right as well as the type annotation. And as I said, we do try to filter this out, but this is not perfect because we simply cannot use the TypeScript compiler for this because the models are not guaranteed to create 100% syntactically valid code. So it is still the case that predicting types makes it a bit more difficult, which can result in the difference between having no type annotations at all and adding extra type annotations. So that's it for research question 1, where we consider type annotations. So in short, it seems like removing type annotations actually improve the performance of these models. So I'll quickly have a sip. For research question 2, we consider the impact of different types of comments. Now, the table on the right once again shows the average metric values in different variants of the dataset. The abbreviations for the CMT, which stands for comment, column, are in order: no comment, single line, multi-line, doc block, and all comments. And if you investigate this table, you'll see that for all models, either the multi-line row or the all comments row has the highest metric values. And in fact, these are always quite close for all models. And this seems to indicate that multi-line comments contribute the most to the performance of these models, but that keeping all comments still yields similar performance. So, so based on the fact that all comments and multi-line comments produce relatively close metric values, you could also say that single line comments and doc block comments may not really help much, but that keeping them does not necessarily have a disastrous effect. So once again, we should have a look at the statistical analysis because the metric values are quite close again, especially for encoder, where we see differences of, well, less than 2 exact match, for instance. And by considering this, we once again get a big table, which you should not try to read. But once again, we see that the differences between different types of comments are significant. For instance, if we compare having no comments to having only multi-line comments, we see a effect size that is, well, for Unixcoder, almost half of the effect size of removing code tokens. So we see a positive effect, but it is a smaller positive effect than the effect of removing all type annotations. And we see a similar behavior with comparing having no comments versus having all the comments. Additionally, we see that single line and doc block comments don't do much. Either they are a bit bad for the models or a bit positive for the models, but in that case, it is with a very tiny effect size. So it seems like these comments simply do not contribute much to the models at all.
Sorry. So
Yes.
I think I already asked that question in Australia, but maybe you have some more information. Did you have a chance to compare all comments to multi-line? Because basically it looks like these two are the best ones. And I don't know, one of the practical outcomes I would like to see is what should I add to my code when I train a model? All comments or simply multi-line ones would suffice.
Mm-hmm. Yes, so we did not directly compare multi-line comments against all comments. We decided to simply stick to one baseline for each research question, which in this case was the no comments. So we compare everything against no comments. to really see what the effect is of adding some type of information versus having no information at all. So we did not compare these, but whether you should have all comments or multi-line comments fed to your model. I would say multi-line comments, but I'll get back to that in a couple of slides, if you don't mind.
Yeah, thank you.
All right, so let's see. So yeah, this is it for research question 2. So what are the explanations for this? Well, for single line comments, it is quite obvious because single line comments are just very small. So you can't really expect a very comprehensive explanation of what some code should do in a single line. And even some people, for instance, use Copilot and instruct it using a single line comment. But in practice, you'll most likely first implement a function. You will give the function a nice name. You give the parameters a nice name. And that information may already be enough to convey what you want to do. And if you were to describe the same behavior in a single line comment, well, the information is so small and so easy to interpret, it may already be obvious from a function signature alone. And aside from this, you also have many directives inside TypeScript code that do not contribute anything to the code, but are used to silence compiler error, warnings or errors, or to silence linters. So yeah, removing these obviously will not have an effect because these simply have nothing to do with the code at hand, but instead instruct third-party tools. As for doc blocks, as you can see in the table on the right, the doc blocks only have a very small effect if they have a significant effect at all. So based on this, my conclusion would simply be that the information contained in doc blocks is obvious. Because if you name your variables well, thinking back to the picture I showed in the first slide, if you name your variables well, then it should be quite evident what a variable or what a parameter should do. And even if it is not that evident, usually you'll already have some code context that may already use a variable, which can still inform a model as to what you're trying to do and give it information so that it can already sort of infer what you're trying to do. All in all, meaning that this doc block is just a bit obvious if you already have the code. As for multi-line comments, their positive effects, I think, can be mainly attributed due to the fact that these are usually used for natural language explanations, which these models happen to be trained on. Well, they have been trained on natural language. And converting from natural language to code seems to be something that they are quite capable at. And if we consider the all comments case, well, this includes multi-line comments. So it seems that the performance is caused by that. And if we look at the difference between multi-line comments and all comments, we see that the effect size is slightly different in some cases. This could be explained by possibly some useless comments taking up space that could have been used for source code tokens instead. Or perhaps if all comments is slightly better than multi-line comments, it could be explained by there being some value when you have information from a single line comment and a multi-line comment, for instance, that there's still a small bit of value added when you combine information. But overall, since these differences are so small, it's really the multi-line comments that are the reason behind the performance we see when using all comments. So to summarize these findings, we see that removing type annotations can improve performance, and that only multi-line comments seem to be valuable to these models. And if we consider these models that have first been trained on natural language and were then trained on code, this seems to make sense, or at least this multi-line comment facet seems to make sense. However, if we consider the training data, it also makes sense that removing type annotations helps them. Because if you remove type annotations from TypeScript code, you'll pretty much end up with JavaScript code. And with the exception of CodeGPT, UniXcoder has already seen some JavaScript code, and Encoder has also been trained on some JavaScript code. So it could be that these models simply already knew a bit how to handle this. But I also want to emphasize with this that this is not, it is not the case that this has biased the models all in favor of the untyped case, because we see similar effects with CodeGPT, and CodeGPT, of course, was not trained on any code prior to our fine-tuning. So what are the implications of this? Well, if we think back to the problem that first motivated this issue, this paper, it was that we do not have much context size, and we want to use it as efficiently as possible. And what we've seen is that the result of removing certain types of information, namely type annotations and different types of comments, actually slightly improves performance. And while these improvements have very small effect sizes, so may have very limited noticeable performance boosts in practice, we can still simply remove this information to make room for other types of information. And well, in this paper, we only investigated these two types of information, but there is so much information that you could use that is all present within these IDEs. And if you can't find anything else to add, you can, of course, always add more source code tokens.
Excuse me, Tim?
Yes.
Do you mind if I ask a question? Actually, I have a couple of questions.
Mm-hmm.
So the first one is, I was wondering, in your experiments, how to what degree were you affected by these models' non-determinism or hallucinations, and to what degree do you think these hallucinations might have affected, you know, the statistical analysis of your findings? So this is my first question.
Okay, so you mentioned both hallucination and what did you say, randomness?
No, yeah, non-determinism, yes.
Non-determinism. Do you mean the same thing with them, or do you mean separately?
Yeah, let's go with I mean the same thing.
All right. So when it comes to non-determinism, let's see. For encoder, we had the choice to configure the temperature. So we purposefully configured a relatively low temperature to prevent very unlikely sequences from being selected. However, I believe we set it to 0.2 to still allow for some creativity in its outputs. And as for the other two models, we used a beam search, and this beam search should also it was configured the same way in each time. So this should limit the amount of randomness that is present in the outputs of these models.
Mm-hmm.
So yeah, is this what you meant?
Yeah, yeah.
All right, great.
Yeah, and the second question is very interesting that, it's interesting, but as you said, it's not maybe necessarily that surprising that removing these type annotations in these dynamically typed languages does not actually improve the performances. So I was wondering if you have like in these projects that you tested on, like what percentage of the text, like how much did you save in that context window just by removing these type annotations?
Okay, that's yeah, that's a good question. That we haven't quantified the amount of tokens that type annotations take up inside of source code. But if we want a rough estimate, I suppose you could take 30% of the number of tokens.
Mm-hmm.
because, or well, in the case of the original data set, because well, 30% of the type annotations. Oh wait, actually, and never mind that. Yeah, we haven't measured that. So that is definitely an interesting thing to measure. That we perhaps should have done, because we want to minimize the amount of useless information in the context window. So quantifying the amount of information we can remove by applying this method is, of course, also an important thing. But unfortunately, I don't have an answer for you right now.
Okay, thank you.
Yeah.
So follow up on that, team. Yeah, thanks for a very nice presentation. And the results are very counterintuitive. I was not expecting these results, but that's why we have this discussion. So I'm wondering, when you remove the type annotations and let's say you save 30% room for more tokens in the context window, did you fill it up with extra tokens, code tokens, or you remove the type annotations and comments and you didn't fill up with any other code tokens? Or I'm just wondering if that could be a possible reason why removing extra information might have produced better results.
Yeah, that's a great question. So our data for our data set, the way we determined where we were going to conduct code completion was by looking at an entire file and then placing a marker in that entire file. So if we do code completion at the end of a file and we remove type annotations, then extra code tokens from the beginning of that file will be in that context window. So indeed, you will have more code context to work with. And if that code context is worth more than the type annotations that you've removed, you could, of course, expect to see better performance.
But you didn't control for the location. You didn't say that. So if it happened that the marker is at the end of the file, then we would have more code tokens, and that might have produced better results. But there are other locations in which the marker was in the middle of the file or in the beginning of the file, right? So you wouldn't benefit from extra room in the window, in the context window, right?
Yes, that's right.
Yeah. I wonder if you can go back to your experiments and actually check this thing. We remove type annotation and instead, we maximize the size of the context. We gave it as much context as we can, and maybe that's what produces better results than adding type annotation. It's just a hypothesis.
Yeah, that's a great follow-up, as you said. Yeah, I agree with you. That's a good next step to make this more solid.
Yeah, and then just a clarification for my own clarity. What do you mean by multi-line comments? Is this a comment that spills over multiple lines, or is this a comment that addresses several lines of code? What's a multi-line comment?
It is the first thing you said. So just a comment that spans multiple lines of code.
Okay.
And repeated single line comments, they do not count. So it's really when you, well.
Okay, good, thanks.
All right. So moving on. Future work. If we look at the results, there's still a lot of other work you can do aside from the things that were mentioned that we can control for. We can also consider many other types of information. So a very interesting thing that could make these code completion models more aware of the local context is well, similar to traditional IDE code completion. We could look through the other files and see what interesting things are in there, such as function signatures, class names, and things like that. And we could embed that in the context, in the input. We can similarly include the file names or the local file structure and folder structure, because this way the model may learn what you have already implemented by these file names alone, or what kind of project it is, because many frameworks, for instance, use a very rigid file structure, in TypeScript at least, which may help it as well. Another interesting thing that could make these models better as you use them is to consider previous predictions. Because if a code completion model gives you a prediction while you're typing and you reject it, in practice, you're giving this model information that it provided you with a bad prediction, which you could also somehow embed into the context window. And you could do many things with this. You could, for instance, have the model check what the user typed instead. So you immediately know, well, this is a bad prediction, this is a good prediction. And then as the good prediction, you use whatever the user typed. And the same thing can be done when the user accepts your prediction. Then the user may still make some modifications, but this is all things that you can include in your context window to make the models adapt over time to suit the user's needs better. So this is things that we can do by adding even more information to the context window. Next, the generalizability can also be, well, the work can be generalized by trying other data sets, other languages such as Python 3, other splitting policies as well, because we split our files on a file basis. You could instead try a repository basis to prevent possible information contained in one in one set of the data from linking to another, so from test to train, for instance. And another interesting thing that I don't really have an answer for yet is to think of a very good way to represent contextual information inside of a graph of some sort, and then to make sure that this is consumable by these language models very well. Yeah, this is a good thing to think about, because if we were able to do this well, then we could, in theory, add all types of information to this knowledge graph, and these models could use it freely. But yeah, just to wrap back to the first point of adding more types of information, namely adding available function signatures. Well, I've done a small experiment that I just wanted to show. So in this experiment, we added a simple comment where we give a lot of type function signatures of available functions in the local project. And we see if this improves a model's abilities to predict function calls to these functions. So I'll quickly go through this because it's well, pretty much another experiment. But we were very limited by context length once again. So for this experiment, we only considered functions that were in the user's own project, and also function calls only to those functions. And we did not include type annotations in this comment. But what we saw was that encoder actually really liked this. In fact, its ability to correctly infer the function name to call improved by almost 10% exact match. And the predicting the entire function, so including arguments, also went up by 7.5%. And it knew to call function at all more often. Yeah, this is just a quick experiment I did for some other work, and just wanted to highlight this because it really shows that there is potential to make the experience that developers have with these language models better and more appropriate to their own work. But this is still limited by context size, so there are definitely still things that we need to research to make this work very well. However, in practice, things are already being done, for instance, by Copilot to incorporate the user's project into code completion. So Copilot already takes into account open windows you have to make the model more educated on your own project. But this is all interesting stuff, and I hope you found this presentation interesting as well. Let's see. Few duplicate slides. Yeah, so yeah, that was it for my presentation. So I would now like to invite you to ask any more questions you have.
All right, thank you, Tim. So as a reminder, folks, we have circa 20 minutes, I guess, for the questions left in our typical time slot. So please raise a hand, write in the chat, grab a mic. whatever we find suitable. And I guess, yeah, Danny, please.
Yeah. So thanks again. Very nice presentation. So you mentioned that for one of the experiments, for one of the models, I think it was Encoder, that you took Microsoft architecture. You took some architecture. You took GPT-2, and then you were able to replicate and train the model. And I'm just wondering, what was your experience with doing that? Because when people talk about training these models, they talk about, this is a very expensive project, endeavor, both in terms of energy cost, GPU, the clusters, the compute architecture that you need to have. Can you comment? Can you tell us a little bit what was your experience with training your own models, just starting off of GPT-2 and a previously published architecture?
Yeah, thank you for the question. It was definitely at first a bit of a challenge, especially as I had not trained the model before. That was made by like a model from some paper. I had not reproduced it before. So I was unfamiliar with the code. And that's the main thing that made it difficult, because they had published all their code. So it was not a terrible experience. But in principle, what I had to do was make sure that their data input matched my the output of the way I prepared the data. And after that, it was relatively simple, because at TU Delft we have a cluster that we can push jobs to. So in the end, what I had to do was simply change a bit of the code published by those authors, then create some scripts to make it runnable on the TU Delft cluster, then upload it and then wait for it to finish. So in the end, it was not too bad.
Mm-hmm. So the information that they provided was detailed enough that you were able to replicate, and although you train completely different language. And
yes,
yeah.
Their reproduction package showed it was quite elaborate, and it showed exactly how they trained their Python and Java models. So I just had to adapt that to my own data set. And I hooked up some extra tools for monitoring, and and it was all it all worked.
And the compute time. So you mentioned a cluster again. It could have been with I don't know what kind of cluster it was, but I'm just curious. Was this something that end up running and utilizing a full powerful cluster for days, or what was the experience?
Yeah. It was quite all right. I used one GPU for each model to train each model, and let's see, for hyperparameter tuning, it took roughly 34 hours per model, because I did not utilize the full data set, as time was relatively short. And for the actual fine tuning, it took around 5 days per model, and that is all on one GPU.
Oh, okay. All right, good, thank you.
Yes.
I guess I'll ask a question then. So basically, one can argue that you found that removing types is beneficial, maybe at least because we get some more space for other information. So did you think about trying removing some of the code tokens, maybe not for the code completion, but say for code summarization? Because I guess some of the tokens are, in essence, like superficial, or maybe they kind of can be uniquely restored, like in C++ when you declare, I don't know, a for loop, there will be an opening bracket or stuff like that. So you can always figure out that it is there, but still it takes some place.
Mm-hmm. Yeah, that's an interesting thing. We did not specifically consider it. But if we're talking specifically about the case of, for instance, an opening bracket, I'm not sure if there's a whole lot to save on context size in that way, because we could, of course, have a special token that delimits code blocks or something like that. But a simple opening bracket is so small that it would also be one token. So it's not something we considered. And I'm not sure how useful it would be, but maybe you can provide a better example that shows that we can actually save quite a bit with it.
I just use an opening bracket because it is kind of the tokens that you can automatically restore that, say, after, I don't know, say a for loop definitions, there would be an opening bracket or stuff like that. So I think, I mean, it is not easy to give it a good set of examples, true, but maybe it is possible to, I don't know, for example, there is like this shorthand notation, which is people sometimes use and sometimes don't, of the kind that a equals a plus 5, which can be replaced by a plus equals 5 or stuff like that. I mean, in the sense that some of the notation, sometimes the code is somewhat redundant, and maybe we can remove some of the tokens without losing the understanding. The code will be maybe not compilable, but it will be comprehensible, even for module.
Right. Yeah, thinking about, yeah, I definitely think that's possible actually. I haven't investigated it, but it sounds like something that could be interesting, especially in JavaScript. It is, for instance, possible to remove semicolons most of the time without making the code syntactically invalid. So that is something you could potentially save on as well. However, I'm also assuming that most of the times the semicolon will already be included with the closing brace token as well. But I definitely think that there is something that can be done in this regard, because it could also be that you translate to some intermediate language, some kind of pseudocode that is very shorthand, and then somehow translate it back in order to save context the tokens when you are running inference. Yeah, I think it's an interesting thing.
Thank you. Any other questions? All right, I guess in this case, let's thank team again for the wonderful presentation, and I will stop the recording now. And I would like to announce that next month we're gonna have a talk by Alexandra Yeliseyeva